Hello there, and this is for BTEC Applied Science. It's chemistry. It's the second assessment objective, which is A2, and it's the second lesson in that series. So the first lesson covered the periodic table in terms of blocks and electron configuration. This lesson is going to cover something called ionization energy and looking at ionization energies against position in the periodic table. We've looked at some trends across periods and some trends up and down groups in terms of ionization energies. So just a little bit more on the assessment objectives then. There's two of them, there's A1 and there's A2, and there's quite a detailed list actually if you do look at the specification, which is a good revision list to use. So this comes from the second objective, and the first video focused on that first box there. So last lesson, lesson 1, focused on understanding the periodic table, that we understood what periods were, we understood what groups were. We also looked at the S, the P and the D block, and that you could identify elements as S, P and D elements, but you could also do electron configuration using the S, P and D notation. So the idea of a 1s2, 2s2, 2p2 for example, that we could do electron configurations. So this lesson is going to focus on something called the first ionization energy, and it will look at the trends in ionization energy across periods 2 to 4 and down the groups 1, 2 and 7. So that's where our focus will be today. Okay, so what is meant by ionization energy? What is the ionization energy? Now the ionization energy, you might recognize part of the word ion. So an ion is something that has a charge, so it's going to be an ion. And the ionization energy, so let's just pick a random element, and I'm just going to use the notation A as a symbol for an element. We're going to turn A into an ion, which is A+. We're going to take an electron from it, and it must be in gaseous state. So that's our definition, is going to be the energy required. So energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions. So that equation represents it quite nicely, but to verbalize it, it would be energy required. This does require energy. It's an endothermic process. Energy required to remove 1 mole, and that's important, it's 1 mole of electrons from 1 mole of gaseous, and they must be gaseous, so it must be gaseous state symbol, 1 mole of gaseous atoms to form 1 mole of +1 gaseous ions. So that's the definition for the first ionization energy. Okay, we do need to know that definition, either by equation or verbally. We need to verbalize it. So energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous +1 ions. It's worth making a note of that definition. Okay, so what affects the ionization? So what's going to make things have different ionization energies? So let me think of what atoms actually look like. So we know that we have a nucleus at the center. So I'm just going to draw a random nucleus here. Nucleus is made up of protons and neutrons. So I've drawn some protons and neutrons in the middle. The nucleus has a positive charge. It has a positive charge, and that's the nucleus. And we know that electrons will orbit in electron shells around the outside. So we have numerous electrons moving around. So I'm going to draw some electrons in this shell. I've drawn an electron in the outer shell. So when it comes to removing electrons, it's the outer electrons that are going to be the easiest to remove. So when you remove electrons, it's this outer electron that's going to be removed. This electron here, the outermost electron, is going to be far easier to remove than these ones. So when we measure the first ionization energy, it's the energy we need to remove this electron. So let's think about it. Why is this electron even there? What holds this electron in place? Well, this electron has a negative charge and the nucleus has a positive charge. So there's an electrostatic attraction between the nucleus and the electron, and that's the force that we need to overcome. So the stronger this force, the more energy is going to be needed to remove this electron. So let's think about the factors that are going to affect the strength of that then. One of the first factors is going to be the radius. In other words, this distance here. The further away it is, the easier it's going to be to remove. The closer it is, the harder it's going to be to remove. The second thing that we need to consider, now the charge on the electron is always going to be -1, but the charge of the nucleus can change because that depends on the number of protons. The more protons we've got, the bigger the nuclear charge. The bigger the nuclear charge, the stronger that attraction will be. So the second factor to consider is the nuclear charge, which is the number of protons in the nucleus. And the third and final point to consider is going to be, and this is one of the harder ones to understand, I guess, is if we think about this electron here that we're removing, it is attracted to the nucleus, but any electrons that are in between, such as this one, any electrons in between will shield the charge. So this electron here is shielding the charge. So we get electron shielding. And that's going to be from the inner shells. So that's from inner shells. So any shells that are inside inner shells. Okay, so those are the three things we must consider when we're trying to compare ionization energy. We look at the radius, we look at the nuclear charge, and we look at the electron shielding. We have to consider all three. And once we've considered all three, we can then try and make comparisons. Let's take a look at our periodic table again then. And let's try and, first of all, I'm going to start with looking down group 1. So let's have lithium and sodium as the first two elements in group 1. Yes, this is hydrogen, but again, hydrogen's not necessarily classed as a group 1 metal. We'll generally see hydrogen over here. So let's compare lithium against sodium. And let's remember those three factors. We've got the nuclear charge, we've got the radius, and we've got the shielding. So there's those three factors to consider. Probably easier if we look at the actual electron configuration. So lithium, if you look at the periodic table, lithium has 3 protons, 4 neutrons, got a mass of 7 and the atomic number of 3. That means that a lithium atom will also have 3 electrons. So 1, 2, 3 electrons. This would be 1s, this would be 2s. So the electron configuration for lithium is 1s2, 2s1. Now, if we look at sodium, sodium has 11 electrons. It's 1123. So sodium again will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. Okay, so if we are going to try and make a prediction of the ionization energy, what we're really doing is we're seeing which electron could be most easily removed, either this one in sodium or will it be this one in lithium. So let's not jump straight to an answer, let's try and compare the nuclear charge, the radius and the shielding. So let's look at the radius first of all. Now the radius, the more shells you've got, the bigger your radius. So sodium having 3 shells versus lithium's 2 shells, sodium has a bigger radius. So I'm going to put sodium has a bigger radius, so sodium is going to have a bigger radius than lithium. Now let's consider the nuclear charge. Nuclear charge. Well, the nuclear charge for sodium is 11 plus. It's got 11 protons, and the lithium is 3. So sodium actually has a bigger nuclear charge than lithium. So that's a bit tricky, that, because sodium having a bigger radius would mean that this is easier to lose. However, the fact that it's got a stronger nuclear charge would kind of counteract that a little bit, maybe. But let's have a look at the third factor. So the shielding. This is the electron shielding, and that's from the inner shells. So this electron for lithium is only shielded by these 2. So it's shielded by 1 shell. However, in sodium, this electron is shielded by all of these shells. It's got more shielding. So sodium has more electron shielding than lithium because it's got more shells. So in conclusion, now we've got to come up with a summary. Sodium's got a bigger radius and it's got more shielding. Despite the fact that there is an increase in nuclear charge, these 2 factors are going to outweigh this one. So it's 2 against 1 if you like. So I'm going to say that my prediction is that the first ionization energy for sodium is going to be less than the first ionization energy for lithium. That's because the attraction is going to be weaker for this electron than it is for this electron with the nucleus, because it's got a bigger radius, it's got more shielding. That's going to ensure that that electron is more easily lost in sodium. So sodium requires less energy to remove the electrons than lithium. So the first ionization energy of sodium is smaller than the first ionization energy of lithium. Looking at the periodic table then, if we want to compare elements as our spec says in group 1, group 2 and group 7, if we were asked to compare the ionization energies of anything within the same group, either group 1, group 2 or group 7, we will use the radius. Now as you go down the group, you move from period 2 to period 3 to period 4, period 5 and so on. As you move down the group, you have more shells. If you have more shells, your radius increases. So as you go down the group, you get a bigger radius. Also, as you go down the group, you have more electron shielding. So as you go down the group, the radius increases, the shielding increases. This means that the outer electron is going to be more easily lost because there's less attraction with the nucleus and the electron because it's further away, because the charge is shielded. So anything below, or the further down the group you go, the easier or the lower the first ionization energy is. So without fail, francium has the lowest ionization energy out of anything in group 1. Rubidium will have a lower ionization energy than potassium, and so on. And that is true for everything in group 1, everything in group 2, and everything in group 7. So iodine, for example, has a smaller first ionization energy than chlorine, and for bromine and fluorine for that matter, because it has a bigger radius, it has more shielding, less energy will be needed to remove that outer electron. So that is true when we look at any group, okay? But our spec does ask us to focus on groups 1, 2 and 7. So when we're asked to compare, give an explanation as well, don't just say. So if you were asked to compare in a question, for example, beryllium versus strontium, don't just say strontium has a lower first ionization energy because it's lower down the group. Don't say that. You need to say that strontium has a lower first ionization energy because it has a bigger radius and more electron shielding. This means that the electron is less strongly attracted to the nucleus and less energy is needed to remove it. So try and give lots of detail in your answers. I'm going to get you to do some questions on these shortly. Time for a task then. So what you're going to do is you're going to compare the following pairs. So for each of the 5 questions, you're going to decide which of those 2 have the highest first ionization energy and explain why. So don't just use the position of the periodic table. You can use that to help you with the answer, but with your explanation, make sure you use the terms radius and shielding. So pause the video, and when you're ready to go through the answers, unpause the video. Okay, so what I'm going to do is I'm going to circle the one that has the highest first ionization energy, and I'm going to give a verbal explanation which should hopefully match what you've written. So for the question 1, the one with the highest first ionization energy is lithium. That's because it has the smallest radius and it has less shielding than potassium. Therefore, more energy is needed to remove the outer electron. And question 2, for the exact same explanation, it's Cl. Cl has a smaller radius, it has less shielding. That means that the electron requires more energy to remove because it's more strongly attracted to the nucleus. Next one, magnesium or calcium. Magnesium is above calcium in the periodic table. That would require more energy to remove the outer electrons because it has a smaller radius, it has less shielding, therefore the outer electrons are more strongly attracted to the nucleus, more energy is needed to remove it. Question 4. Fluorine is the answer. And the explanation gets quite repetitive, doesn't it? Because it's the exact same explanation. Fluorine has a smaller radius, it's got less shielding, therefore the outer electron is more strongly attracted to the nucleus and more energy is needed to remove it. And finally, question 5, the answer is sodium. The exact same explanation, because it has smaller radius, it has less shielding, therefore the outer electron is more strongly attracted to the nucleus and more energy is needed to remove it. So just be careful, because this question was looking for the highest first ionization energy. The exam question could ask you for the lowest first ionization energy. It's the exact same argument, but obviously your answer would be the other ones, and your explanation would be the exact same, that it has a bigger radius and more shielding, therefore weaker attraction. So it's the kind of the same argument, but just be careful on highest or lowest. Okay, so that's looking down the groups 1, 3 and 7. What we also need to be able to do is to compare periods 1, 2 and 3. So what happens to the ionization energy as we move across those periods? Okay, so let's start with the first period, I guess. Let's look at hydrogen versus helium. And we're going to use the exact same logic. We're going to look at the radius. Now remember, the radius is going to be driven by the number of shells and the nuclear charge. We're also going to look at shielding and nuclear charge. Those were the 3 factors that we must consider. Right, let's look at helium and hydrogen then. So hydrogen literally has 1 electron. So hydrogen is 1s1. Helium has 2 electrons, so will be 1s2. So when it comes to the shielding, their shieldings are very similar. Or we can get away with saying the same. So they have the same shielding because they have the same number of shells. So same shielding because they have the same number of shells. So the shielding is going to be the same. It's equal. Now the radius, this is tricky, this one, because it's tempting to say the radius will be the same. But actually, because they have the same number of shells, doesn't mean they have the same radius. If they've got the same shells, so let's have a look at helium has a 2+ nucleus, hydrogen has a 1+ nucleus. They have the same number of shells, but because the charge is greater on helium, those shells are actually pulled a bit closer. So actually, if we were to draw the radius, I'm going to overemphasize it now, the radius of helium will be smaller than the radius of hydrogen, simply because it's got a bigger nuclear charge, it can pull the electrons closer. Okay, so now let's think about the energy needed to remove an electron from here or to remove an electron from here. Well, helium has a bigger nuclear charge. It also has a smaller radius. So helium has a smaller radius, a bigger nuclear charge, and the same shielding. That means that more energy will be needed to remove this electron than to remove this electron. So our general trend as we move across a period is that the ionization energy increases. So as we go across the period, the ionization energy increases, and that's because the shielding remains the same, the radius decreases, and the nuclear charge increases. Nuclear charge, remember, is the number of protons. As you go along the periodic table, you see the nuclear charge increase, and we'll have a look at that in the next slide when we look at the periodic table again. Let's look back at the periodic table then. So this time we are just purely looking across period 1, across period 2, and across period 3. So across the period, you remain in the same shell. So hydrogen and helium are in the same shell, so same shielding, and nuclear charge increases. This has a nuclear charge of 2. Look, it's got 2 protons. That has a charge of 1. So across the period, the radius decreases and the nuclear charge increases. Therefore, the attraction of the nucleus with the outer electron increases. So helium is going to have a higher first ionization energy than hydrogen. And we can say that generally, and I'm saying generally because we are going to look at a couple of exceptions in a minute. So generally, as you go across from lithium to beryllium to boron to carbon to nitrogen and along here, as you go along, the general trend is the radius decreases, the nuclear charge increases, the shielding remains the same. Therefore, the ionization energy increases because it has a stronger nuclear charge with a smaller radius. It's more attracted to the nucleus, it takes more energy. Think about it, as you go across the period, the atoms get smaller and smaller, and the charge at the nucleus gets stronger and stronger. That means any outer electrons to be removed are harder to remove. I've really overemphasized it with the sizes here. So the nuclear charge increases, the radius gets smaller. So as you go along the period, they become more difficult to remove. The ionization energy increases across a period. So just to remind us, as we go down the group, ionization energy decreases. As you go up the group, ionization energy increases. We saw that in the last 5 questions. And the general trend for a period, as you go across the period, ionization energy increases because the radius gets smaller, the nuclear charge increases. Time for the task then. So what you're going to do, similar to the last task, is you're going to identify which of the two has the highest first ionization energy. So again, I'm asking for the highest. Just be careful there. So pause the video, and when you're ready to go through this, press play. But remember, what we're doing is we're using the position in the periodic table, but to explain it, we're using shielding, nuclear charge, and radius. So you must be able to look at your periodic table and look at those 3 trends. So pause the video, and when you're ready to go through it, press play. So like last time, I'm going to circle the one with the highest and I'll give an explanation. So lithium versus beryllium. Well, they're in the same period. However, beryllium has a bigger nuclear charge, a smaller radius, and they have the same shielding. So therefore, it has a bigger ionization energy. Because it has a smaller radius and a bigger nuclear charge, therefore the electron is more attractive to the nucleus. Oxygen or fluorine. Again, they're in the same period, but fluorine has a higher nuclear charge and a smaller radius, therefore higher first ionization energy. Sodium or magnesium. Again, they're in the same period. Magnesium is further to the right, which means it has a smaller radius, has a higher nuclear charge, and therefore more energy is needed to remove the outer electron. Chlorine or argon. Again, they are in the same period. However, argon is further to the right, which means it has a smaller radius and a higher nuclear charge. They have the same shielding, so argon has a higher first ionization energy. Carbon or boron. Now, carbon is to the right of boron. They're in the same period, therefore they have similar shielding. Carbon has a bigger nuclear charge and a smaller radius, therefore the outer electrons are more strongly attracted to the nucleus and therefore a higher first ionization energy. Looking back at the periodic table then, I did say that was the general trend, okay? Because we do see some exceptions, and I'm going to label where those exceptions are. So the general trend from lithium to beryllium all the way through to neon is that the ionization energy increases. So the general trend is an increase. However, between beryllium and boron, there's actually a slight drop. And likewise, so between here and here, there's a slight drop. And likewise, between here and here, there's a slight drop. So it's awkward that between groups 5 and 6, we get a slight drop. And between groups 2 and 3, we get a slight drop. We need to be aware of this. So going from magnesium to aluminium, we actually have a drop. And going from beryllium to boron, we actually have a drop. And also going from nitrogen to oxygen, we also have a drop. And going from phosphorus to sulfur, we have a drop. And we need to be aware of those. And also, which is more tricky, we need to explain. Okay, so I'm going to start by explaining. The good news is the dip from magnesium to aluminium is explained in the exact same way that the dip from beryllium to boron is explained. So that's the same explanation, which is good. And likewise, the drop that we see from nitrogen to oxygen, we explain that in the exact same way that we see the drop from phosphorus to sulfur. So we just need to know these drops, but we need to explain them as well. Right, let's have a look at why we have a drop from beryllium to boron and why we have a drop from magnesium to aluminium. They are explained in the exact same way. So what I'm going to do is I'm going to do the electron configuration for beryllium, which is just 1s2. So beryllium is 1s2, 2s2, has 4 electrons. So beryllium is 1s2, 2s2. 1s2, 2s2. Boron, however, has an extra electron and is in fact 1s2, 2s2, 2p1. So for some reason, this electron here is more easily lost than one of these electrons here. So this electron is easier to remove than this electron, and that's because it's in a new subshell. It's in the p subshell, and the p subshell is higher in energy. It's more easily lost. So that blip between beryllium and boron is explained using the p subshell. It's going to a new p subshell. And it's the exact same reason with magnesium and aluminium. Magnesium is 1s2, 2s2, 2p6, 3s2. So that's magnesium with 12 electrons. So magnesium is in fact 1s2, 2s2, 2p6, 3s2. Aluminium has an extra electron, and as you can see, the aluminium, 1s2, 2s2, 2p6, 3s2, and 3p1. So the exact same explanation here. It's due to the p subshell. So aluminium, the outer electron is in the p subshell, which is easier to remove than the s subshell because it's higher in energy, it's further from the nucleus. So that explains those blips between magnesium and aluminium and beryllium and boron. Looking back at the periodic table then, we've explained why we've got a drop from here to here, because we're going from the new to a new subshell. We're going from the s subshell to the p subshell, which the electron is higher in energy, it's more easily lost. So that's why we have a blip from beryllium to boron and from magnesium to aluminium. We also need to explain why there was a drop here. Now we can't use subshells here because they're all in the p subshell. This is the p block. So let's have a look at what's happening with nitrogen and oxygen and phosphorus and sulfur. I'm going to explain the nitrogen and oxygen one because sulfur and phosphorus is exactly the same. So let's look at the reason for the blip between nitrogen and oxygen. Nitrogen has 7 electrons, oxygen has 8. So nitrogen, 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. Oxygen has 1 more electron, so I'm going to draw that there. Will be 1s2, 2s2, 2p4. So this time we're trying to explain why the electron is easier to lose in oxygen, because there's a blip, it goes down to oxygen, it goes against the trend. And that's because this electron is being removed from oxygen, and this electron, because it's being forced to pair up with this electron here, it has electron pair repulsion. So this electron, because both electrons are negatively charged, this electron kind of gets kicked out by this electron. So it's easier than you would imagine because it has a helping hand. It's got repulsion from this electron here. So oxygen is easier than expected because of electron pair repulsion. So electron pair repulsion. So let's go back to the periodic table and we'll have a look at that blip. So the blip here then between nitrogen, oxygen and phosphorus and sulfur. So the general trend is you get an increase in ionization energy as we go across the period. However, we get the drop here and the drop here. We explained that using a new subshell, and we explained the drop from nitrogen to oxygen or phosphorus to sulfur due to electron pair repulsion. So the drop between 5 and 6 is electron pair repulsion. The drop between 2 and 3 is the new p subshell, which is higher in energy. Time for the final task of the video then. So here we've got 10 questions and I've got a mixture here. So they might be in the same group, they might not, they might be in the same period, there might be an exception to the rule, the ones we've just looked at, so be careful here. Okay, so have a go at these. Pause the video now, and when you're ready to go through the answers, press play. Right, so here we're looking for the highest first ionization energy. So question 1, I identify the two elements, lithium and potassium. I can see that they are in the same group. It's probably worth pointing out that these questions are impossible if you don't have a periodic table. You are given the periodic table in the exam. Okay, so you're not expected to know this off the top of your head. You must have a periodic table in front of you, and if you don't, then get one and maybe start the questions again because you would have found them very difficult. So lithium and potassium are in the same group. However, potassium is lower down the group, so lithium has a higher first ionization energy because it has a smaller radius, has less shielding, stronger attraction. Now carbon and boron, they're in the same period, so I've got to be careful. Are they exceptions? No, they're not. Right. So carbon has a bigger nuclear charge and a smaller radius. They have the same shielding, therefore carbon has a stronger attraction. Number 3, magnesium or strontium. Now they're in the same group. The groups are dead easy. So magnesium has a smaller radius, it has less shielding, therefore stronger electrostatic attraction to the electron and a higher first ionization energy. Question 4, Cl and S. They're in the same period. Is it the blip where the blip? No, it's not. So I'm safe from the exception. So I'm going to say that chlorine has the highest first ionization energy because they have the same shielding. It has a smaller radius and a higher nuclear charge. So chlorine requires more energy to remove those outer electrons, or the outer electron. Calcium or potassium. Locate those in the periodic table and you will see that calcium, they're in the same period. However, calcium is further to the right, which means it has a smaller radius. It has the same shielding, has a higher nuclear charge, and more energy is going to be needed to remove those electrons. Moving on to number 6, silicon or phosphorus. Now, is that the blip? It's not the blip, okay? So they're in the same period. Phosphorus is further to the right. It's got a higher nuclear charge and a smaller radius, therefore a higher first ionization energy. Number 7, B or BE. Oh, this is the blip here, because if you just followed the trend, you might be tempted to say that boron has a higher, but it doesn't because we have the blip here between groups 2 and group 3. So actually, the highest of the two is beryllium. So it goes against the trend here. It's beryllium, and my explanation for this is because boron's outer electron is in the new subshell. So despite the fact it has a high nuclear charge, the answer here is Be, because the outer electron for boron is in the new subshell, which is higher in energy. N or C, and here in the same period, it's not the blip, it's not where we have the exceptions. Nitrogen has a smaller radius and a higher nuclear charge, therefore higher first ionization energy. Number 9, aluminium or magnesium. That's where the blip, we have a blip there. So the answer here goes against the trend. The answer is magnesium, and that's because despite the fact that aluminium has a higher nuclear charge, the outer electron in aluminium is in the new P subshell, and magnesium is still in the S subshell. And the last one, F or I. Here, they're in the same group. F is further up the group. It's got a smaller radius and it has a smaller, less shielding. So it's less shielding, it's got a smaller radius, therefore less energy is needed to remove the electron in iodine than is needed in fluorine. There's a stronger attraction in fluorine, smaller radius and less shielding. I'm actually going to give you 2 more questions, 2 bonus questions. I'm going to ask you to compare nitrogen and oxygen and sulfur and phosphorus. You've got 2 bonus questions here because I'm feeling generous. So pause the video again and have a look at those 2. Okay, so nitrogen and oxygen, they're in the same period. However, oxygen has electron pair repulsion. So this is looking for those exceptions there between groups 5 and 6. So the highest here is in fact going to be nitrogen is the highest, because despite the fact that it has a smaller nuclear charge, oxygen is easier than expected due to electron pair repulsion, and we use the exact same theory for the next 2. Sulfur has electron pair repulsion, which makes it easier, so the ionization energy for phosphorus is greater than sulfur. That's all for this video then. Hopefully that was useful. Let me know what you think. Again, any other videos that you'd like, please get in touch and let me know.